The next question, that is question number 23. The question is, the total number of positive integral solutions of the inequality 15 less than x1 plus x2 plus x3 less than or equal to 20 is first option 685, second option 785, option C, that is the third option, is 1125, the fourth option, that is option D, is 570. Let us examine which is the correct option. What is the given inequality? 15 less than x1 plus x2 plus x3 less than or equal to 20. He has given like that. Therefore, the expression x1 plus x2 plus x3 is surely ahead of 15 and cannot exceed 20. That is less than or equal to 20 and greater than 15. Well, to have the answer for this question, let us create one more variable, say r, like that. x1 plus x2 plus x3 is equal to 16 plus r, where r is equal to 0, 1, 2, 3, r, 4. Why is it necessary to write 16 plus? This expression x1 plus x2 plus x3 is surely greater than 15 and we want to have a positive integral solution. Therefore, the least value of x1 plus x2 plus x3 is 16 and of course the largest value will be of course 20. So to mean it, to understand it, to have it, I have introduced another variable, say r. Well, if you take r is equal to 0, this will be 16. If it is 1, it is 17. If it goes up to 4, then x1 plus x2 plus x3 reaches 20. Therefore, this situation and this situation can be viewed similarly, can be observed same. Therefore, we find to have the solutions for this. Of course, here we are supposed to have the positive integral solutions, but here we are supposed to have non-negative solutions, non-negative integral solutions for this. Hence, the total number of such solutions will be 16 plus r minus 1 c 3 minus 1, as in minus 1 c or minus 1 type. In that type. So it is 16 plus r minus 1 c 3 minus 1. This is equal to sigma r is equal to 0 to 4. 16 minus 1 is 15. So it is 15 plus r c2, r running from 0 to 2. And if you can simplify that, if you take r is equal to 0 to 4. If r is equal to 0, it is 15 c2, next 16 c2, next 17 c2, next 18 c2, next 19 c2. And if you add all of these things, you will be going to have the answer to be 685. That is the very first option, that is option A is the correct answer. You please understand the style of converting this inequality into a suitable equation, so that we will be ready to estimate the number of either non-negative solutions or positive integral solutions according to the situation. As the situation demands here to have the non-negative integral solutions, we could have made use of this formula. Okay, well, so the answer is 685. That is the first option is the right option. The next question is, that is question number 24. There are 12 pairs of shoes in a box. Then the possible number of ways of picking up 7 shoes, so that there are exactly 2 pairs of shoes. How many shoes are there? 12 pairs of shoes are there. 12 pairs means 24 shoes. Out of them, you are supposed to have 7 shoes. In those 7 shoes, 2 pairs of shoes must be there. The remaining means 3 shoes. Those 3 shoes, among those 3 shoes, no pair must exist. This is the situation. Well, what are the options given? The first option, that is option A, is 63,360. Second option is 63,300. Option C is 63,260 and option 4 is 63,060. Let us now have a look over that. How many pairs are there? 12 pairs are there. Out of those 12 pairs, you can have 2 pairs in 12C2S. How many? 12C2S. So far, we have selected 4 shoes. Still, we have to choose 3 shoes. These 3 shoes, among these 3 shoes, no pair must be formed. Okay, out of 12 shoes, 12 pairs, 2 pairs are selected. Still, 10 pairs are there. Out of those 10 pairs, 10 shoes with respect to the left leg, 10 shoes with respect to the right leg. You can choose 3 shoes among all left-legged shoes or 3 shoes among all right-legged shoes, or one left shoe and 2 other right shoes, or 2 left shoes and 1 right shoe among the remaining, not the combination of these 2. All these can be very easily observed to be in 10C3 into 2 cube ways. Total 12C2 into 10C3 into 2 cube. The answer comes to be 63,360 if you can calculate. Therefore, the right option among the options is the first option. Option A is the correct option. The next question is, that is question number 25. If A, B, C are 3 natural numbers that are in AP, such that A plus B plus C is equal to 21. Then the possible number of values of the ordered triplet ABC is. How many such ordered triplets ABC can be formed? That is the question. What are ABC? Basically natural numbers, provided they are in AP. What is the third condition? A plus B plus C is 21. Bearing these 3 conditions in our mind, we are supposed to frame triplets ABC, ordered triplets. How many such triplets can be formed? We shall see. Options given are, option A is 15, option B is 14, option C is 13, and option D, that is the fourth option, is 17. Let us examine. What are the conditions? A, B, C belong to N. And then A, B, C are in AP. What is the third condition? A plus B plus C is equal to 21. Now let me take A is equal to B minus D, B as B itself and C as B plus D. Why is it necessary to consider them like that? Why? Because these 3 form an AP according to the data. He has said it. Therefore, you add these things. What are you going to have? A plus B plus C is equal to B minus D, B plus D. If you add all these things, you will be having 3B. But from data, A plus B plus C is 21. 21 is equal to 3B. Therefore, B is equal to how much? 7. Middle number is 7. Middle number is 7. And if you are supposed to have A and C, B is got. One more thing, A, B, C are all natural numbers. Therefore, the difference in this AP must also be an integer. Must also be an integer. Well, take the difference to be 0. Then 7, 7, 7. This is one triplet. If the difference is 1, 6, 7, 8. If the difference is 2, 5, 7, 9. Next triplet, 4, 7, 10. Next triplet, 3, 7, 11. Next, 2, 12. Next, 1, 13. Stop there. Why? Because A, B, C are all must be natural numbers, isn't it? Well, count these triplets. 1, 7, 13, 1 triplet, 2, 3, 4, 5, 6. 6 triplets. You see, 6, 7, 8 triplet is different from 8, 7, 6 triplet because it is ordered. Therefore, with these combinations, how many triplets you can observe? 12 triplets. Besides that, and more triplet, that is 7, 7, 7 is also there. Therefore, how many such triplets are possible to be observed? 13 triplets you can frame, you can construct such that these 3 conditions are satisfied, namely ABC must be natural numbers, ABC are in AP, and A plus B plus C is 21. With those 3 conditions in our mind, we are able to frame, we are able to construct 13 ordered triplets. Therefore, the number, the correct answer among the given options is option C, that is 13 is the right answer. Now let us turn our head to look towards question number 26. The next question, that is question number 26. 5-digit numbers are formed using the numbers 0, 1, 2, 3, 4 and 5 with repetition of the same digit in any number. Then the number of numbers that are divisible by 3. Option A is 1080, option B is 2160, option C is 540 and option D is 4320. These are the given options. Let us have a look over the data. What is required? 5-digit numbers are to be formed. What are the digits given? 0, 1, 2, 3, 4 and 5 are the digits given. Is the repetition allowed or not allowed? Allowed. With the repetition of the same digit, any number is allowed. Then the number of numbers that are divisible by 3 is. How to get it? Let us first of all get the idea of forming the numbers. How many digit numbers are required? 5-digit numbers are required. That is, you are supposed to fill 5 places. Five-digit numbers. So 5 places are to be filled. The first place can be filled in how many ways? In the first place, 0 is not allowed because if you have 0 in the first place, it cannot be considered a 5-digit number. It can be called a 4-digit number only. Therefore, you are not supposed to allow 0 to enter in the first place. Therefore, the first place must be a non-zero digit. Hence, it can be filled in 5 ways only. It can be filled in 5 ways only. What about the remaining places? This place, no restriction, 6 ways. This place, no restriction, 6 ways. Third place, no restriction, 6 ways. Now, you stop there. Why did you stop there? Still, a place has been kept vacant to fill up. Why? Because we are supposed to frame a number divisible by 3. How can you say or how can you believe that a particular number is divisible by 3? If the sum of all the digits present in that number is divisible by 3, then the total number is divisible by 3. We know. Well, we have filled only 4 places. The sum of all the digits in these 4 places may fall in 3 cases. What are the cases? Sum is in the form 3n, 3n plus 1, 3n plus 2. Only 3 cases. Sum of the digits in the first 4 places which we could have already filled may occur in 3 cases. Either in the form 3n, or in the form 3n plus 1, or in the form 3n plus 2. Exactly one and only one of these cases happens. Only one of the cases happens. Well, let us see. If the sum is in the form 3n. This is already divisible by 3n. So here we fill then the last place, by either 0 or 3. 0 or 3. How many ways? 2 ways. Why? Because 3n plus 0 divisible by 3. 3n plus 3 also divisible by 3. In the first case, how many possibilities are there? Only 2 possibilities are there. What are the possibilities? Either 0 or 3. Okay. Let it be in the form 3n plus 1. So, it leaves a remainder 1 when divided by 3. Well, in this case, the last place can be filled by how many? If you put 2, it becomes 3n plus 3 divisible by. If you put 5, 1 plus 5 is 6, then also it is divisible by 3. So, 2 or 5. The last case. 3n plus 2. If the sum of all the 4 digits, which we could have filled earlier so far is in the form 3n plus 2, then observe the digit, it is 2. To have the total divisible by 3, you are supposed to have here either 1 or 4. Either 1 or 4. Here 2 ways, here 2 ways, here 2 ways. Would you like to have all the 3 cases, or exactly one of the cases, or at least one of the cases? If at least one of the cases, it becomes 6. Exactly one of the cases we are supposed to have. Therefore, only 2. Hence, the last place can be filled in 2 ways only. Total, what will be the answer? So, answer is 5 into 6 into 6 into 6 into 2. 6 cube is 216. 5 2s are 10. 216 into 10. What will be the answer? 2160. So what is the right answer? Second option, that is option B, is the correct answer. 2160. Here one may get confused here. Here we are having 3 cases. Here 2 possibilities. Here 2 possibilities. Here 2 possibilities. Then 2 plus 2 plus 2, 6 it may be. No, exactly one of the cases should happen. Not all the 3 or either of them. Exactly one of them. Therefore 2. Hence the answer is 5 into 6 into 6 into 6 into 2. That is 5 into 6 cube into 2. That is 216 into 2 becomes 2160. The option B, second option, is the correct answer for this question. The next question, that is question number 27. There are 2010 chairs round a table. They are numbered 1, 2, 3, 4, etc. up to 2010. They are numbered chairs. The number of ways in which 5 persons can be seated in any 5 of these chairs, so that the number of empty chairs between any 2 consecutive persons must be same. How many chairs are there? 2010 chairs are there. How many persons are to be seated? Just 5 persons are to be seated. Therefore, definitely 2005 chairs will be kept vacant. Of course, the condition that has been given here is the number of empty chairs between any 2 consecutive persons must be the same. How many persons are to be seated? 5 persons are to be seated. The number of spaces, number of empty chairs between any 2 consecutive persons must be same, he is saying. Okay, let us divide 2010 by 5. What are you going to get? 402. It is 402. With 402 gaps, you arrange the 5 persons as they are marked, as they are numbered, that is, as the seats are specified. They are not to be counted circular, they must be linear only. It can be arranged in 5 factorial. Therefore, so total number of such arrangements will be 402 into 5 factorial. 402 into 5 factorial, that is 402 into 120 must be the answer. We need not expand this because in every option that 5 factorial is a common factor, and among the available options, the first option, that is option A, is the correct option. 402 into 5 factorial is of course the correct answer. The next question before us is question number 28. The number of positive integral solutions of the equation xyz is equal to 105 such that x not equal to y not equal to z, that is they are all different, is first option 24, option B is 27, option C is 6 and option D is 12. What is the basic equation given for us? X, Y, Z is equal to 105. Is equal to 105. Positive integral solutions of the equation we want to have. So X, Y and Z, all of them are supposed to be positive. First of all, let us observe the canonical form of 105. What is 105? Here 105 is equal to 3 into 5 into 7. Therefore, we have to distribute 3, 5, 7 or their multiples in as form of a triplet, say x, y, z, such that the product is 105. And x, y, z are all different. Well, what will be the positive possible cases? Let us observe. Moreover, they are all different. You should not take 135, 105. You are not supposed to take. How? 1, 3, 35. That is one possibility. 1, 5, 21. That is another possibility. Product is 105. These are distinct. Product is 105. These are all distinct. Another possibility is 1, 7, 15. Here also it is 105. One more possibility is 3, 5, 7. One more possibility. So these are the possible combinations of the factors x, y and z such that they are positive and distinct also. Moreover, with these three natural numbers, how many triplets you can form? 3 factorial. Here 3 factorial. Here also 3 factorial. And in the last case also 3 factorial. So what is the total number of arrangements or the ways of forming the triplets? 6, 6, 6, 6. 4, 6 are 24. So what is the right option? Option A is of course the right option. That is 24 ways we can arrange x, y and z so that they are pakka positive numbers, exact positive numbers and different, of course, factors of 105. Hence the answer is option A, that is 24. The immediate question before us is question number 29. There are 15 different apples and 10 different pears. How many ways are there for Jack to pick an apple or a pear, and then Jill to pick an apple and a pear? You have to understand the situation very, very carefully. In one particular sentence, R or R is used, and in the second condition with respect to Jill, and is used. You must be very careful. What are the options? 23 into 150, 33 into 150, 43 into 150, 53 into 150. 150 is a common factor of course among all the 4 options given. Let us now see. What is the situation? How many apples are there? Here, 2 transactions are there. One with respect to Jack and the other with respect to Jill. What does Jack do? Jack picks an apple or a pear. At the same time, Jill picks an apple and a pear. First of all, Jack picks up an apple. You imagine. Then he picks up an apple in 15C1 ways. Then Jill enters into the field. What is his duty? He should pick up an apple and a pear. How many ways he can do? Already one apple is selected, 14 apples are remained. So 14C1 into 10C1. One pear he should select. This is the first case. Jack picking up an apple first. What is the duty of Jack? He is supposed to pick an apple or a pear. Next, the other possibility. Jack picks an apple. Picks up an apple first. This is the part. Now, Jack picks up a pear. How many ways he can do that? There are 10 pairs, he can do that in 10C1 ways. Now also Jill enters into the fray. What is his duty? He is supposed to pick up one apple and one pear. Well, 10C1. What about apples? Are there any selections previously? No. 15 apples are safe. Out of those, he picks up one apple in 15C1 ways. And how many pears are left behind? Only 9. Why? Because Mr. Jack picked up one pear already. Therefore, it is 9C1. So, we should have either of these, either this, or exactly one of them, either of them. Therefore, the total answer is this plus this, and that comes around 23 into 150. Why should I have that? 15C1 is 15, 10C1 is 10, 10 into 15, 150. So it is 14 into 150. What about this? 10C1 is 10, 15C1 is 15, 10 into 15 is 150, 9C1 is 9. So this is 9 into 150. If you add these two, what are you going to have? 23 into 150. 23 into 150. Therefore, the first option, option A, is possible. And the answer is 23 into 150. That is option A. Here, you may have to understand the propositions given or and. Jill does two things at a time. What are things? He picks up an apple and a pear. But Mr. Jack does any one of those, either this or that. So the number of ways must be added here. Hence the answer is 23 into 150 is the correct answer. The immediate next question before us is question number 30. The total number of integers n such that 2 less than or equal to n less than or equal to 2000 and HCF of n and 36 is 1 is equal to. That is, you are supposed to collect natural numbers lying between 2 and 2000. Between 2 and 2000, how many such natural numbers will actually be there? 1999 natural numbers will be there. Out of these natural numbers, how many are co-prime to 36? That is relatively prime to 36. Relatively prime in the sense their HCF must be 1. There must be no common factor between them other than 1. Such things we are supposed to collect. Well, first of all, let us see 36. What is 36? This is 4 into 9. That is 2 square into 3 square. What are the general factors for 36? 2s, 3s, 6s, 12s, like that. Well, now let us collect the numbers from 2 to 2000 which are multiples of 2, which are multiples of 3 and which are multiples of 6. let us now avoid all those things. If you avoid multiples of 2, multiples of 3 and multiples of 6, the remaining numbers will have a common factor HCF with 36 as 1 only. That is the clue here, that is the main thing that we have to catch here to make an attempt in the correct way. Yes, of course. So what is the duty before us? First of all, we are now ready to collect multiples of 2, multiples of 3 and multiples of 6 in the present domain. There is between 2 and 2000. Number of multiples of 2 in 2 to 2000 is the integral part of 2000 2 by 2, how much? 1000. Again, number of multiples of 3 in 2 to 2000 is by 3. This is 666. This is the we are interested to gather the multiples only. That is why we would have counted found the integral part of 2000 by 3. In a similar way, the number of multiples of 6 in this interval is equal to 2000 by 6. This will be are these valid numbers or invalid numbers in the present collection? These are invalid. We want to have the natural numbers which are relatively prime to 36, that is which have the greatest common factor, that is HCF as 1 with 36. Therefore, we have to avoid multiples of 2, multiples of 3 and multiples of 6 also. Therefore, the required number of numbers is what is the total number of natural numbers in the present domain, that is 2 to 2000? 1999, 1999 minus 1000 plus 666 plus 999. You avoid all of them. What are you going to get? 666 is the right answer. Is the right answer. Therefore, among the given options, the first option is of course the right answer, and the plan of attacking on the question to get the required answer is very important here, as the required number must be relatively prime, that is that should have highest common factor 1 with 36. We are supposed to avoid multiples of 2, multiples of 3 and multiples of 6. Hence the answer is first option, that is option A is the correct answer. The next question before us is question number 31. How many combinations can be made up of 3 hens, 4 ducks and 2 geese, so that each combination has hens, ducks and geese? Words of same kind are all different. How many combinations can be made up of these collection? The options among them are first option is 305, the second option is 315, the third option is 320 and the fourth option, that is option D, is 325. We may have to recollect a good discussion and a formula from combinations. if P things are alike of one kind, if Q things are alike of another kind, R things are alike of some other kind, then the number of ways of choosing any number at a time is P plus 1 into Q plus 1 into R plus 1 minus 1. If there are n different things, then if there are n different things, then the number of ways of picking up any one at a time is 2 power n minus 1. That is 1 plus 1 into 1 plus 1 into 1 plus 1 n times into 2 power n minus 1. That is avoiding all of them. That selection is avoided. Therefore, it is 2 power n minus 1. Here, we may have to apply the same consequence here also. There are 3 hens. Consider the first hen. You can choose or you cannot choose. Second hen. Again 2 things, 2 combination, 2 chances. Third, 2 chances. Out of all of them, 2 into 2 into 2. 2 cube options will be there. Minus 1. Why should you put minus 1? Why should you put minus 1? The option of avoiding the hens is to be subtracted. Therefore, corresponding to hens, the number of ways of choosing is 2 cube minus 1. And corresponding to ducks, how many ducks are there? 4 ducks are there. It is 2 power 4 minus 1. And corresponding to the third variety also, it is 2 square minus 1. This is a well-known and famous result from combinations. We have seen it for so many number of times. Therefore, the answer is this. Let us now get it simplified. What is 2 cube? 8 minus 1 is 7. What is 2 power 4? 16. 16 minus 1 is 16 minus 1 is 15. What is 2 square? 4 minus 1 is 3. 7 15s are 105. 3 into 105 is of course 315. Therefore, what is the correct answer here? 315 is the right option. 315 is the right option. That is the option B. The main thing that you are supposed to make use of here is the formula 2 power n minus 1. When n distinct things are there, the number of ways of choosing any number at a time, that is the number of empty collection is avoided, of course, is 2 power n minus 1. Here there are 3 such varieties. In the first variety it is 2 cube minus 1, and in the second variety it is 2 power 4 minus 1, and in the third variety it is 2 square minus 1. The total number of such combinations is just nothing but this, that is 315 is the right answer. The next question is question number 32. The question is the number of ways of selecting 10 balls out of an unlimited number of white, red, blue and green balls is. Total number of balls to be selected is 10. The number of ways of selecting 10 balls out of an unlimited number of balls. So how many different kinds of balls are there? White balls, red balls, blue balls and green balls. Green balls. Well, the total number of ways is required. The first option is 270, second option is 84 and the third option is 286. Fourth option, that is option D, is 86. Let us examine which option is the right option. Let me name, what are different colors? White, red, blue and green. Let the number of white balls selected be x1. Let the number of red balls selected be x2 and those blue balls be x3 and green balls be x4. x4 is with the similar okay. In total, how many balls are to be selected? 10 balls are to be selected. Therefore, what should you have? x1 plus x2 plus x3 plus x4. What is the total number of balls? It is 10. It is 10. Well, the number of ways of selecting 10 balls out of an unlimited number of white, red, blue and green balls. Here, you may not choose red balls. You may choose 9 blue balls, 1 green ball, like that. As a whole, you are supposed to have 10. That is, we are supposed to have number of non-negative solutions of, non-negative integral solutions of this equation x1 plus x2 plus x3 plus x4 is equal to 10. Yes, according to the known formula, it is 10. What is the answer? Answer is 10 plus 4 minus 1 c 4 minus 1, that is n plus r minus 1 c r minus 1. The number of non-negative integral solutions of the equation x1 plus x2 plus x3 plus etc. xr is equal to n is nothing but n plus r minus 1 c r minus 1. We know it pretty well. There is a famous result, rather formula, that can be used at so many instances of that case, this sort. Hence the answer is 10 plus 4 minus 1 c 4 minus 1, that is 14 minus 1 is 13. 13 c3. Is it given? Of course, they have been expanded. Let us do that also. What is 13 c3? Therefore, the answer is 13 c3, and among the options it has been expanded. Let us do that also. The 13 c3 is nothing but 13 c3 is nothing but 13 into 12 into 11 by 3 factorial, that is 6. It goes 2 times. 2 13s are 26 and 26 11s are 260 plus 26 is 286. Therefore, the third option, that is option C, is the right answer. The next question, that is question number 33. The number of different order triplets ABC, where A, B, C are integers such that these can represent sides of a triangle whose perimeter is 21 is. Here he has given A, B, C belong to I. I is the set of integers. Integers means they can be negative also. Such idea enters into our mind. But in the immediate next sentence he has said that these numbers can represent the sides of a triangle. They cannot be negative. Therefore, we have to take it for granted that A, B, C must be natural numbers. A, B, C must be natural numbers. Moreover, A plus B plus C is, the perimeter is 21, he is saying. That is A, B, C. What are A, B, C? Natural numbers which can be represented as the lengths of the sides of a triangle with perimeter 21. What is the perimeter? A plus B plus C is therefore 21. A plus B plus C is of course 21. Well, but as ABC are the lengths of the sides of a triangle, we can use A plus B greater than C, B plus C greater than A, C plus A greater than B. That is what we call the famous triangle inequality. In any triangle, sum of the lengths of two sides is strictly greater than that of the third side. Therefore, we must have A plus B greater than C, B plus C greater than A, and C plus C greater than B. Let us make use of one of those. B plus C is greater than A. Implies A plus B plus C is greater than 2A. Implies 21 is greater than 2A. 21 is greater than 2A. Implies 2A is less than 21. Implies A is less than 21 by 2. What is 21 by 2? 10.5. Implies A is less than or equal to 10. A is less than or equal to 10. A is less than or equal to 10. Isn't it? Because A, B, C are all natural numbers, we have A less than or equal to 10. By considering B plus C greater than A, we could have taken that A is less than or equal to 10. If you consider C plus A greater than B, A will be able to have B is less than or equal to 10 and C is also less than or equal to 10. C is also less than or equal to 10. Therefore, what should happen? 1 less than or equal to A, B, C less than or equal to 10. A, B, C less than or equal to 10. With that restriction, we are supposed to have A, B and C. How many such possibilities are there? Therefore, we have noticed that A, B, C are all natural numbers and moreover, those three numbers A, B, C lie between 1 and 10. Okay. ABC are the sides of a triangle, hence we have three different cases. What are the cases? Let us now discuss with that. Case 1. A greater than B greater than C. In this case, how many are possible? How many triplets are possible? 10, 9, 2. A plus B plus C is 21, isn't it? 10, 8, 3. 10, 7, 4. 10, 6, 5. Next, 9, 8, 4. 9, 7, 5. 21. 1, 2, 3, 4, 5, 6. If at all 10, 9, 2. 10, 8, 3, 10, 7, 4, 10, 6, 5, 9, 8, 4, 9, 7, 5 and then 8, 7, 6. 8, 7, 6. These are the possible cases 1, 2, 3, 4, 5, 6, 7. And in each case, every combination gives rise to 3 factorial ordered triplets. 3 factorial, 3 factorial, 3 factorial, 3 factorial, 3 factorial. So, in this case, number of triplets is equal to 7 into 3 factorial. 7 into 3 factorial. What is 7 into 3 factorial? 3 factorial is 6, 6 sevens are 42. This is about case 1. Now case 2. Case 2. A is equal to B greater than C. A is equal to B greater than C. Let us see. The first case 10, 10, 1. Is it possible? 20 greater than 1, okay. 11 greater than 1, okay. 11 greater than 10, okay. Next, one more thing. 9, 9, 3. Next, 8, 8, 5. 9, 6, 6. 6 plus 6 plus 9. Okay. A is equal to B greater than C. Here in these 4 cases, what will be the number of triplets? This is 3 factorial by 2 factorial. This is 3 factorial by 2 factorial. This is 3 factorial by 2 factorial. That is also 3 factorial by 2 factorial. All together this is 4 into 3 factorial by 2 factorial. This is 6 by 2 is 3. 4 into 3 is 12. Now, the last case, there is only one case. Last case, there is only one case. What is that case? Equal. A is equal to B is equal to C. Equilateral triangle. There is only one. What is that? 7, 7, 7. That is one triplet. How many triplets are there? This is 42. This is 12. 54 and 777. Another combination is also there, and there will be no more triplets with that combination. So total number of such triplets will be 42 plus 12 and 1. What is that 1? 777. In the case of an equilateral triangle, it also gives us a triangle, equilateral triangle with the perimeter 21, of course. Therefore, the total number of such triplets becomes 55. Hence, the answer is C. That is the third option is the right option.